Umang, and this is joint work with Zheng Li, who was an undergrad student, and this is part of the thesis that he did with me, and it follows after a previous paper that was also published at Uppsala last year. So what is this paper about? Oh. Yeah, so this paper is about this problem called linearizability monitoring, which effectively asks, you're given an execution of this kind, which is, you can think of it as an execution coming out of the implementation of a concurrent data structure, and you're required to check if you can come up with a linear sequence which sort of explains this. This problem as such is NP hard because think about it, you have to really enumerate all possible interleavings of all the operations to be able to determine this answer. And so in this paper, we're trying to reinvestigate this complexity boundary. And we show that for a very large class of data structures, which pretty much cover most important data structures, you can actually refine this complexity boundary. And we show that, in fact, you can come up with algorithms that run in this sort of a complexity upper bound, which is something like a big function in K. Think of it as an exponential function in K. K is the number of processes in your history, and some polynomial in N. So this is, in some sense, better than a very vanilla NP hardness result. Okay, because if I just have NP hardness, the only thing that I can guess is that it may take exponential in the length of the history, and this result basically says that that's not the case. Which means that if you actually have a fixed number of threads, then the scalability is polynomial in the length of the history. Okay, so for those of you who may not know what linearizability is, here is an example. So this is an implementation of a hash map, and it is supposed to run across multiple clients. So there are three different functions that this data structure implements. And I don't think I have the time or the interest to go through the entire example, but the broad outline is that if there are multiple clients who are trying to invoke this different functions here, they may interleave in strange ways, and if your implementation is not careful, you will get some really, really weird answers. Okay, and as such, this is yet another concurrency error, but when it comes to data structures, one can actually specify a very nice property, and that's what linearizability is. So linearizability is a way to specify correctness of data structures, which are implemented in a concurrent manner. And it basically says that you first figure out what is the specification of your sequential implementation of the data structure, and then if you want to determine if your implementation or some particular execution is linearizable, you just check if that execution can be explained by certain points, and these points will now constitute a sequential run of the sequential specification. If you can manage to come up with such a sequence of events and which explains the behavior, that's when it is linearizable. And for the same reason, if you look at the second execution over there, it's not a linearizable implementation of a stack. It's not a linearizable execution of a stack. That's because the only way you can linearize these things is when you do push 1 and then you do push 2 and then you do pop 1, which is not a valid stack behavior. Okay, so roughly, linearizability of an implementation asks if all histories coming out of that implementation are linearizable, meaning you can always find a linear sequence that is equivalent to the history, the concurrent history. So that's the definition of linearizability. And if you've been following any amount of work in PL conferences about linearizability, there's a lot of focus on the problem of verifying concurrent implementations, and it turns out to be a very difficult problem for a lot of reasons, including the fact that your specifications can be very complicated. And when you talk to people in the industry who actually build these data structures, they nonetheless go for a more practical take. They try to test these implementations, think of it as a very giant fuzzer that is testing these implementations. And as part of these testing, this testing, one has to effectively answer this question. You're given a history, and you want to check if that history is linearizable. So that is the monitoring problem that I'm looking at. As I said, the general problem of linearizability monitoring is an NP-hard problem. And this hardness result applies to very simple specifications like register specification. And very recently, there have been some works on coming up with restrictions on the kinds of histories that you have, so that you can get polynomial time algorithms. But in general, if you don't have these restrictions, the problem cannot be solved in polynomial time. Right. So the question that we're trying to answer is, can we take another look at the complexity boundary? Meaning we're not trying to restrict the histories, but we're only trying to understand if I can come up with better algorithms than exponential time algorithms. Okay, so these are our results. We show that for a large class of data structures, which I'll soon talk about, you can actually solve this problem in FPT, which is an algorithm that runs in time f of k multiplied by some polynomial in n. K is the number of threads. And we show that, in fact, you can view all of these linearizability monitoring problems through a very simple unifying framework. And that framework is something that is a problem of over graphs, and that routinely comes up in very different PL problems, including static analysis. And we also implemented our algorithms and show that they also work very well in practice. I realize I've already spent 8 minutes just talking about the background. So that's our input. You have a history with you, and you're given a specification. Think of it as stacks or queues. And the history has n operations and k threads. And you're required to answer whether there is a linearization of this history that explains the behavior of the history. Okay, so let me first talk about this generic framework. So here one tries to look at this graph. I call this graph the frontier graph. So if I have a history like that, from there I can come up with this sort of a graph. The nodes of these graphs are sets of operations. These are ideals in the sense that every such set in this graph is downward closed with respect to some kind of partial order that I can infer from the history. And now, and the edges represent addition of one event. And the main reason why I want to formulate this problem using graph reachability is that if I look at that graph, it's exactly all the paths all the paths in the graph are exactly all the linearizations of the history that I have. And in particular, if I am looking to solve the linearizability problem, I just have to check if there is a path in this graph which belongs to my sequential specification. Right? So linearizability monitoring boils down to this problem. So you have a graph, and you want to check if there is a path in the graph that belongs to some language. So this is called the language reachability problem. And the most interesting aspect about linearizability is that unlike other similar problems in concurrency, the size of this graph is actually very nice. It is linear in n, the length of the execution, the number of operations, and it is exponential only in the number of threads or processes. And that happens because the histories that you get are effectively are something called interval partial orders. And based on my previous slide, it follows that if I can find a polynomial time algorithm for this language reachability problem, I will automatically get a FPT algorithm for linearizability monitoring. So that's the essence of the rest of the talk. So I'm going to try to find classes of data structures for which language reachability can be solved in polynomial time. All right, so the first class of data structures that satisfies this is order oblivious data types. And the definition is roughly the following, The definition says if you have a data structure is said to be order oblivious if whenever you take two legal sequential specification executions of the data structure and they are simply permutations of each other, then they both land in the same state. By state, I mean something like the internal state of the data structure. For example, over here, if you look at these two executions, they're both valid, and they're both permutations, and they both land into this common state where the element stored in the priority queue is just the singleton set 5. Okay, so that is why I call them order oblivious. And there are a lot of data structures that very naturally satisfy this restriction. And then we showed that we can also extend this definition and add other data structures like registers. And this is a very mild extension of this data structure. Alpha is some sort of a parameter. And it roughly says that on top of them being permutations, they also have to have the same behavior on some extra automaton that you have on the side. The theorem now that we have says that for this class of data structures, you can also solve linearizability monitoring in FPT time. So alpha is that extra parameter, n is the number of events or operations in your history, and k is the number of threads. And this is just some details about the algorithm, which I think I'll not talk about. But this algorithm is roughly some sort of a graph search algorithm. Okay. Yes. So the next class of data structures is context-free data structures, and stack is one such data structure. If you have ever encountered static analysis papers that talk about CFL reachability, the idea is pretty much the same. So if I look at a data structure like stack, it is definitely not an order oblivious data structure, which is the class that I talked about a little while ago. In fact, it is not alpha OODT, no matter what alpha I pick. So what do we do? Well, we come up with a new class of data structures for which language reachability is nonetheless polynomial time solvable, and that's the class. So we call this CFL ADT class, and the formal definition roughly says that if you can come up with a grammar for your specification, then the data structure is a CFL ADT. So as an example, for the stack data type, this is the grammar. It says, it's the routine push pop specification, except that the grammar can have as many rules as the number of values in your history. Okay. So because the problem of CFL reachability on arbitrary graphs is solvable in cubic time, it follows that for this large class of data structures, linearizability monitoring is also solvable in FPT time, because the graph itself is fairly large this time. Okay, so we show that you can actually further improve this result for the specific class of stack data structure, for the stack data structure, and if you sort of carefully observe what are the constants and how large is the grammar and what is the shape of the grammar. So this is not so important. If you're interested, please go and look at the paper. That is the most interesting aspect of the talk. We also show that for the Q data structure, you can still solve this problem in FPT time. The reason why this is, so by the way, Q is this specification. I'm just describing the specification as a label transition system. Okay, and the labels on this, the sequences of this, the sequences that are admitted by this label transition system are constitute the Q specification. Okay, so this is the usual thing that you would anyway imagine. The reason why this is a big deal is because the problem of checking whether there is a path in the graph, which is according to the Q specification, for arbitrary graphs, this is an undecidable problem because it sort of very closely resembles reachability in Turing machines. Even for DAGs, for arbitrary DAGs, this is a NP-hard problem. So we need to do something else. Oh, these slides are GPT generated, and now it messed up the figure here. The core idea behind this algorithm is the following. It relies on this very simple algorithm for checking if a sequence is a Q sequence. Okay, so suppose I have a sequence of NQs and DQs, and I want to understand if it is actually a legal Q sequence. Here is a linear time streaming algorithm, except that you have 2 pointers. The way you're going to process the sequence is as follows. You'll maintain 2 pointers. One is the current pointer, which always advances 1 step at a time. And there is this other pointer front. It sort of lags behind, and it intuitively represents the front of the queue. So for example, in the beginning, both of them will be at the beginning. And then I will advance current to the point when I will first advance it to peak 1, and then I will advance it to NQ2, and then again peak 1, and so on. The reason I can advance curve so far is because the front is at a place where I have NQ'd 1. As soon as I DQ 1, I will have to advance front all the way until NQ2. And that represents, that is the way to update what is the current front of the queue. So this algorithm actually runs in linear time, but it uses 2 pointers. So you can actually formulate this algorithm as some sort of a rewriting relation. R is a relation on pairs of sequences, and it roughly represents the same algorithm. And the core lemma is that this rewrite relation is effectively going to give you the Q specification. All right. I don't think I should go into all this, but the point is that once you have nailed down this rewriting relation that represents the Q specification, you can actually lift it and formulate an analogous problem for the entire frontier graph. And you can check membership in this relation in polynomial time. And that's why Q monitoring can also be performed in FPT time. Let me also talk about the evaluation aspects of the paper. So we looked at some very standard data structures that were publicly available, and we compared against previous tools that were also trying to solve this problem, but in a very vanilla manner, and also other tools that were trying to solve this problem under certain restrictions. And we showed that our tool does reasonably well, and it sort of grows not too bad as compared to the number of operations in the history. And with respect to when it comes to number of threads, the scalability is also not too bad. I think that is the end of the talk. We gave a unifying framework for linearizability monitoring algorithms. And we show that for a very large class of data structures, indeed, this bound applies. And we have a tool that is publicly available. So if you have any questions, I'd be happy to hear them.
We have time for one question while the next speaker sets up concurrently.
So can you give me an example where is there a common data structure that is actually whose monitoring problem is exponential in the history size?
Meaning it's not FPT?
Yeah.
So for example, there are data structures like DQ, for which we don't know the answer. I mean, we tried, but we couldn't solve it.
Okay.
Oh, sorry.